Yeah, that's pretty old things I did maybe 30 years ago or so, but still perhaps interesting to show. So what does it mean? Before I start with these Monte Carlo things, I wanted to make one point clear, because one of your colleagues asked me yesterday what I'm going to speak about when I speak about Monte Carlo for radiation damage. Is not this software SRIM or TRIM, which you perhaps know. I forgot what this TRIM stands for. Transport of rapid ions something, and SRIM is a later version, stopping and range of ions in materials. It's a software commonly used by people doing these irradiation experiments to determine how many defects you create and which depth you reach, how many defects, Frankel pairs and so on you obtain and so on. It's also a Monte Carlo code, very old. I think it's from the 70s or so. When I was looking for it yesterday, I found a reference as they claimed to have rewritten the whole code from Fortran to BASIC in 79 or so. And it's regularly updated, and I think there are still newer versions. So whenever you use this software, you're supposed to give the year from which you took the software. So I don't know where they are now, but typically people give it's calculated with SRIM or TRIM 2005 or so, because apparently these results are not so stable against modification. I don't know. I never used this software. So this is not what I'm going to speak about. I wanted to speak about what we call driven systems. So systems which, besides the thermal jumps, also undergo force jumps, which is often the case. I will give some simple examples. I mean, one example would be under irradiation. Another also could be plastic deformation. And I want to show first with some not too simple analytical models that apparently you have this competition between thermal jumps and force jumps, that there can be a kind of equilibrium between these two, and how to describe it. And this goes back to what we learned in the very beginning, this statistical mechanics stuff. So I will revert to this. But before, I wanted to show a simple analogy. Perhaps you remember this little animation I showed here, that systems tend to go to equilibrium, mechanical equilibrium or so. And now imagine that besides this mechanical driving force, you have another driving force which constantly, once in a while, pushes up your ball here. I tried to make something like this here, so it's pushed up and down. And this way, you will reach a kind of stationary state. This compromise between, if you call it thermal tendency towards equilibrium, and then besides this athermal forcing away from equilibrium. And it's always interesting whether we find a stable state in this type of systems. And for this, I went back again to my very first slides. I think it was lecture 2 or so. I omitted this part. I found it too complicated at this point, but it's very instructive to go through it. In this initial lecture, I showed this example of B2 ordering. So you have the ordered BCC lattice with one species sitting on the corner sides, the other species on the center side. And you can write down a pretty simple mean field approximation for the free energy. Doing so, you find a phase diagram, you find the disordering temperature and everything. Now you can approach this from another point of view. And the very nice thing is that it leads precisely to the same results. The even nicer thing is that this approach can be generalized. So maybe we don't go through all the lines here, but the basic idea is now you write down a kinetic equation. How many A atoms are sitting on the alpha sublattice, how many are sitting on the beta sublattice, or I call it better this alpha and this beta. Okay, this characterizes the degree of order. And for the temporal evolution, you can have jumps from here to here, or vice versa. So the change in this occupation is given by the number of, or probability for jumps from sublattice alpha to the other one, and so on. And this is given here by simple kinetic equations. It's the jump rate times the probability that you find an alpha atom on an A atom on side alpha times the B atom on side beta, if we consider AB exchanges. So this decreases the number of alpha A atoms on the alpha sublattice. This increases it. So overall, and for the thermal jump rate, you have this thermal activation term here. And if you translate everything, these occupations, into an order parameter between 0 and 1, that's very simple calculation, you end up with such an equation here. So the change in order parameter is given by this simple function of the order parameter. Okay? So here's the idea. Okay. And I think I have a slide on this. Yeah, this is better. So here you can look at this curve, this polynomial for different temperatures. And you see that above the critical temperature, that's a blue curve, the evolution goes towards this order parameter 0. Precisely at the critical temperature, yeah, you see here is a kind of saddle point. So it will move in this direction. And here, for temperature above the critical temperature, yeah, perhaps I should explain it a bit more. If this ds dt is negative, this means for positive s, it decreases, so it moves upwards here. Here, if ds dt is positive, it means it moves in this direction. So it approaches this stable point here. Yeah? If you are here, it's negative, so it will move upwards here. So we have a stable point here. And one can calculate the stable point, and the result is precisely what we obtained from the mean field thermodynamic description. But the big advantage of this approach, this kinetic approach, is that now we can introduce these extra jumps. So imagine a system with vacancies or these AB exchanges or whatever. So you undergo the thermal jumps, plus once in a while you undergo forced jumps. So I add just to these jumps from alpha beta, I have the thermal jumps plus the ballistic jumps. And same for these. So this equation is only slightly modified. And then going through all the algebra, you can construct a kind of phase diagram. So here we have the temperature, but here now we have this rate of ballistic jumps. Yeah? So it's a bit normalized here, so I took out some thermal factor and I normalized it to the here. Oh, sorry, that's the wrong way around. This should be ballistic in the numerator and thermal in the denominator. I normalize these. Okay, so this is this axis here. What does it mean? Here at very high temperature, or above the critical temperature, these temperatures are normalized to the critical temperature. The system would undergo disordering from both, yeah, from the thermal and from the ballistic side. So it's not very amazing that this goes down to 0 here. So here we have disorder. This line is broken because I copied it from some PDF. Yeah, so this should go down to 1 here. So here we have disorder. But now if you go into this field here. You have this competition between ballistic and thermal jumps, but here apparently the thermal jumps win, so you retain the ordering. But here at very low temperature, because the thermal jumps become so rare, the ballistic side wins. Yeah? So here you get a disordering again. There's even more in this. If you look here, I think at some point this becomes a first order transition instead of a second order transition, and here's a critical point, and lots of things. You can play the same game for the FCC lattice, the L12 ordered structure on the FCC, but the shape of this curve is very much the same. There are also further enhancements of these ideas, this is denoted by this L, which are not that important. So that's the basic idea. And the question is, can we believe these simple analytical models, or should we do it a bit better? Here, marked here, you have the athermal disordering, here you have the thermal disordering, and here you find a region of stable order. You find stationary states. Yeah? You find I would not call it equilibrium, but a stable state of order. Equilibrium would mean that it is thermal. Yeah? So, as I said, there are many assumptions in this analytical system, analytical model. Among others, we assume that the system is completely homogeneous, and so on. So what I did is I put down a Monte Carlo code, and besides our thermal jumps with a vacancy, I once in a while do a forced exchange. So and regarding these kinetic equations, it's obvious. Yeah? I just add this probability for athermal exchanges. Okay? And that's why it is very, at least useful, to use the residence time algorithm. From the residence time algorithm, we have a kind of natural time scale. Yeah? And now we can say every now and then we make a ballistic jump. Yeah? There's an important remark here, which is true for all these driven systems, that the detailed balance condition, which we introduced more or less precisely some time ago, is not fulfilled. Detailed balance means that the probability for a forward exchange times the number of systems in this state equals the backward process. No? Detailed balance we use to give some condition for the jump rates. Yeah? Here we have to put a physical system, but it's the same already whenever you consider kinetic or system evolution. Yeah? If you are studying system evolution, kinetic Monte Carlo, you anyhow have to care for how you choose your transition rates. Yeah? Whether you use a saddle point or just an AB exchange, this completely changes the system behavior. Yeah? And that's even more important here in these driven systems. So here's the simple idea. You have the vacancy jump rate as before, with some thermal activation. Here's saddle point minus initial energy. That's delta E, so that's what we had before. And then I sum up the times for all these thermal jumps. And if a certain threshold is reached, then I do a ballistic change, and then I continue the thermal. Okay, now I have to go back a few slides. I changed my slides. So here. So how do I model these ballistic jumps? I had different things or different approaches. The idea is to use or to model high energy electron irradiation. It's not that good for ion irradiation. The reason is if you do ion irradiation, that's seen here in this slide here, you intermix a huge region. So here in such a what we call collision cascade, you do an extremely strong perturbation of your system. So what I did here is to model a kind of electron beam irradiation. What happens here is that you kick out one atom and you shift forward a row of atoms of say 5 or 10 atoms. Yeah? If you would not do so, what you do here is you create a vacancy. Here you create an interstitial, and they would recombine directly. Yeah? And I also varied the size of these displacement chains here. This was one way to model such type of systems. I did another thing, which is perhaps a bit more brute force, also to model severe plastic deformation. I don't know whether you're familiar with these severe plastic deformation processes. I mean, you all know plastic deformation, rolling, forging, and so on. These severe plastic deformation, they reach deformation states of several 100%, basically by recovering the initial shape. So there's this ECAP process and what is it called? This rotational deformation and other things. High pressure torsion, right? And also ball milling, I think in the 80s and 90s, ball milling to create non-equilibrium alloys was very fashionable. So everybody did ball milling. You put a powder or two powders of whatever material into such a ball mill. You have spheres and they rotate in a vessel, and these spheres, they hit your powder particles, and then they forge and are fractured and so on. And this way you can intermix and perhaps stabilize all kinds of structures. So I tried to model this with a similar idea, so that I do shearing on a, in this case, FCC slip plane once in a while, which also means that you destroy the state of thermal equilibrium every now and then. Yeah? So the idea is that you shift one or shift the material along one Bogas vector here. Due to the periodic boundary conditions, I had to shift this back in this initial position. So here are some results for the simple case of, I took here the L12 structure, the FCC lattice. Where I did such ballistic exchanges every 10 to the 5 time units or so. Here you see the Monte Carlo time in the units of this residence time algorithm. And you see here the degree of long-range order as a function of temperature, or here as a function of time for different temperatures. You clearly see that here, this part here on the left is for rather low temperature, this part is on the right-hand side for high temperature. For low temperature, below 400, under these conditions here, it's completely disordered. And now if you raise the temperature, you achieve some stable ordering. That's what we expect from this simple analytical model I showed. So this is the athermal part, where the athermal exchanges win the game. Now here at elevated temperature, 1600, 1800, and so on, you see that here, say at 1810, still there's some stable degree of order, and here it's approaching zero order. So here you have a clear disordering. This, of course, you can run for different values of this ballistic jump rate. And you can construct a phase diagram. For the degree of order as a function of temperature here. For different values of this ballistic exchange rate. Yeah? So you see here you have 0 order. Here order goes up to 1, perfect order, and here disorders again. Now if you increase this ballistic jump rate, you see that this region of stable order shrinks further and further. So you obtain such a behavior as we expected from the analytical model. I did not show this, but maybe one sees it here. It appears at least as if this is also a first order phase transition. Yeah? It's a very abrupt change in order. Yeah? It's always hard to say whether an order, whether a phase transition is first order, second order in Monte Carlo, because this was 30 years ago. The system size still was pretty small. I think I used 40 by 40 by 40 atoms. So to distinguish between a first order transition where the degree of order abruptly jumps from 0 to a finite value, or whether it's gradually for such a small system size is not absolutely clear. But here, at least at the high temperature, I would say it's clear. Here it jumps from this 1810 degree of order 0.5 to close to 0. And here you see this also this very steep increase at least. Yeah. Okay, and then, as I said, I tried to apply this also to severe plastic deformation or whatever you call it. I did two different things. One was the same, this ordering-disordering transition, and it looks very much the same. So again, you find a transition from ordered to disordered. This is just an example here where I plotted not only the long-range order, but also the short-range order. That's something you don't have in these mean field models. I don't know whether you are familiar with these terms. Long-range order means that you have a periodicity over distances much larger than the lattice constant. Short-range order means that you have a preferential environment, so that if you have L12, that the aluminum atom is preferentially surrounded by nickel atoms. That's short-range order. And here, yeah, I studied the structure factor, which is basically the super lattice reflection here. I did this also for a precipitating system. And I introduced this cluster dynamic model here some days ago, yeah? Where instead of doing a full Monte Carlo, you only consider the number of clusters containing so many B atoms. Yeah? So the size distribution, if you like. Yeah? And this graph I already showed for increasing time. This maximum here moves to the right. So the clusters grow as expected. And I also showed, I think, this graph here that you obey here for sufficiently long times this nice scaling behavior. That's the same set of curves here is on the left side, but I normalized it here to the average size, and I normalized this to the maximum, so that all the maxima fall on one point here. You see that all these curves, they lie on one master curve here. Now I took the same model. This is basically here the shrinkage rate, which I introduced in the other lecture. So the probability is that a cluster containing n B atom loses one atom. Oops. The other one is just this capture rate. I did not write it down again. So this is the thermal probability that an atom is emitted from such a cluster here. And here I added such a ballistic term. This is multiplied with the size of the cluster because this effect, of course, is much more pronounced for a larger cluster as it is for a smaller one here. And this I can again plug in to calculate the evolution here. And you see a similar set of curves as before here. So that's a very early state. No, which one is a very early? Probably this one is a very early state here. So you start to form precipitates here. And the average size or the maximum of this curve here moves slightly to the right. But here it's not a scaled function here. Now it settles at a stable function here. Yeah? Which is also what we expect. I mean, you have your set of precipitates. They grow by the thermal growth. And then once in a while, from this external forcing, you take out atoms. Yeah? So this is seen here, that you reach a kind of stationary distribution. Here, that's in German, sorry for that. You see the average size here, the solid line, which goes to seems to go to a stationary value here, and the precipitated volume fraction goes down here continuously. And I did the same. I mean, here again, we have a couple of assumptions. If you do such a cluster dynamics model, I did the same for with the Monte Carlo. And I just show a few slides here. You see cross sections for different time steps. Here you see how these clusters in the beginning grow. But here, apparently, they reach a stable value. Stable does not mean that the system freezes. It still evolves in time, but the rate of athermal to thermal processes cancel out. Yeah? And here, these are these size distribution, these cumulative size distributions, which more or less approach a kind of stable state here. Yeah, you can play a lot with these systems here. So this is now for different values of this ballistic time interval between two forced jumps. You see here, it should go, of course, constantly up. If it is infinite, there are no ballistic jumps. But here you see that it clearly reaches, so it's the average cluster size here, it reaches a stationary value here. And the shorter this time interval between two ballistic jumps, the smaller the average size becomes. Okay, so this was, so to say, kind of outlook what one could also do. There are two things I like. I mean, of course, it's a complete toy model, yeah? But allows to control what you are doing. We had this analytical model in the Monte Carlo, allowed to go beyond the assumptions, but to verify that what we did in this analytical model was not completely stupid. That's one point. And from a more practical point of view, it also shows that using these type of models, you're also able to study systems what they are not initially made for. Yeah. So it offers a lot of freedom, so to say, these type of computer simulations. Okay, so this was my nearly last presentation. Any questions about that? If not, I can show few slides where I try to summarize a bit my ideas about what we can do. I mean, I already went a bit in this direction. Monte Carlo versus molecular dynamics. What can we do, what can't we do? This slide I already showed in the very beginning, I think in the introduction or so. Just shows the distance which can be overcome by thermal jumps over a certain time, or here it's, I think it's here. That's the diffusion distance. And here we compare to some physical distances here. Elastic displacements, lattice vibrations, are in the order of a tenth to a hundredth of a lattice constant. So in the range of 0.1 to 0.01 angstrom. Atomic distances, as you all know, are in the range of few angstrom. Precipitates, what you normally use for peak hardening if you are if artificial aging. You have sizes in the range of 50 nanometer, depends on the alloy, perhaps 100 nanometer, but not typically not micrometer or so. The grain in polycrystal is 1,000 times larger. That's this scale. And here you see this, what I said, this diffusion distances at different temperatures. So what can we expect to model using different approaches? Now this I already showed. So in here, that's what I also already showed here. Molecular dynamics, you have millions of atoms up to microseconds. Monte Carlo, millions or even more, but you can simulate much longer times. And then we have both ends of this hierarchy. For even smaller systems, higher precision, you can do DFT ab initio. Few atoms, maybe up to 1,000 or so. It depends on the code. This VASP code, I think it can handle up to several thousand of atoms, but it's difficult. Normally with DFT, you obtain ground state structures. This means 0 Kelvin, more or less no excitation in the material. Yeah? Still, you can determine forces, restoring forces. So in a harmonic approximation, you can determine phonon modes or so, lattice vibrations. So what you obtain from DFT, ground state structures, so which crystal structure is the most stable one, for example, what's the energy of a vacancy, what's the R for dislocations and grain boundaries is already difficult. Elastic properties, since this is only small displacements. And very important, you can use DFT to generate input for interaction potentials. I showed one of these examples, these neural network potentials, where they generate a huge set of configurations using DFT, and then more or less fit using these neural networks, fit parameters to this to these energies and so on to get more or less realistic interaction potentials. Yeah, at MD we already heard a lot about it. Yeah, can be used to study atomic dynamics, lattice vibrations, single atom jumps. For example, using this NEB method, melting, adhesion, crystal growth from the melt, and also relaxation processes. I think I showed this example of a dislocation splitting and so on. But all things which happen on a time scale, yeah, microseconds is already pretty heavy. I would say better nanoseconds or some nanoseconds. Always keep in mind a typical MD time step is in the order of femtoseconds. So to reach a nanosecond, you have to do 1,000,000 time steps. To reach a microsecond, you have to do 1,000,000,000 time steps. And each time steps requires the integration for each atom. So if you have 1,000 atoms, you have to do, for a microsecond, you have to do 1,000,000,000,000 of integration steps. Monte Carlo in this sense is much simpler for a huge number of atoms, since you skip all these microscopic relaxation processes. Yeah? You can do millions of atoms or even much larger systems for a very long time. In particular, using this residence time algorithm, if you go to low temperature, the probability for a thermal jump becomes extremely small, which means that the time step becomes extremely long. Yeah, I love this example of aluminum copper, where at room temperature the probability, no, the distance a copper atom can move in 1 hour or so is in the range of picometer. Yeah? But in Monte Carlo you don't care, because if you do residence time algorithm, yeah, you can cover, I don't know, millions of years or so. So what is it good for? Kinetic of phase transformations, kinetics of diffusion, but mostly we do it on a rigid lattice. And then what I did not add here, of course, from this you can go to even more coarse-grained models, like phase field, like finite element, like whatever you like. Yeah? And these methods, MD and MC, can be used to generate input data for these continuum models. Yeah? So we have a hierarchy of different models, and each has its pros and cons. Each is appropriate only for a certain choice of questions. Yeah? Yeah? But if you combine them, you can get into, I mean, that's now, yeah, slowly I would say, upcoming what we call multiscale modeling. Yeah? You start with DFT, then step by step you go to coarser and coarser time scale, time and length scales, and then at the end you still hope that you achieve a more or less realistic picture of your material. So here is the interrelation, as I understand it. If you combine DFT and MD, you can get ab initio MD. MD with MC, we heard about that during this MD run, once in a while you do a Monte Carlo step. In this combination, to me, it's not very clear what the time scale is. I mean, in MD, you have a very well-defined time scale. But for these in particular in the grand canonical ensemble, you have no appropriate time scale. So if you do the transformation of a copper into an aluminum atom every nanosecond or every picosecond, yeah, it's not clear to me. So it's maybe people more clever than me have an answer on this. And here, how we can exploit or how we can combine these methods. I also showed examples for this. I mean, DFT, yeah, for example, generate input data for potentials in MD, but DFT also, this I also showed, to generate input data for this cluster expansion for Monte Carlo, yeah, where you have this pretty large set of pair, triple, quadruple interactions between atoms to construct a more realistic Monte Carlo model as we would have just with pair exchanges. or per interaction energies. And I think that's my last slide here. These are all things I hope you got here during this course here. Of course, there's much more. What is this word by Feynman? There's much more at the bottom also. So perhaps you have questions or comments on this. It's my personal view here on this kind of atomistic modeling we presented here during this 2 weeks. Yeah, any comments or ideas or questions? And I'm sure the future is in these combined methods, multi-scale modeling. You cannot expect to do molecular dynamics for seconds or even longer times, because, I mean, even with, I don't know how many core systems and so on, it's out of sight that we can cover these realistic timescales. So you have to do something. Yes, please.
In DFT, how is the time involved? Like in one of your slides, you mentioned time involved.
Yeah, in DFT, I think you have no real time. I mean, it's ground state properties. What you do is just to minimize the overall electronic energy, and from this you get the electron density distribution, which then can be translated into total energies or so. Artificially, or I don't know whether it's artificial, if you have energies, gradients in energy are forces. And you can derive forces in DFT, what is Feynman forces, or I forgot the precise name. Yeah, so you slightly displace the atoms from the equilibrium position, which generates forces. And if you have a force, you can, for example, use Newton's equations of motion to relax the atoms. Yeah? But still, I mean, there's this method which is called ab initio MD. There you do something like this. So you do in molecular dynamics, but generate the forces from a DFT model for each time step, which again, of course, is very heavy. Yeah. So that's, and that's what I meant by this time scale, which is accessible there. Probably it's more appropriate for molecular systems. So if you want to study the properties of a smaller system as a solid, I mean, here in a solid, we have certain advantages that the systems in most cases are more or less periodic, but the systems have to be pretty large to get realistic properties. In a molecular system, I don't know, water molecule consists of 3 atoms, so you have more freedom. So, and I think even for biomolecules, which are pretty large, I mean, say thousands of atoms, you can still do it. But a priori, there is no time in DFT.
Finite temperature properties in that possibility?
Yeah, they try to, again, using a similar approach, they calculate forces, and then you can calculate harmonic potentials or harmonic lattice vibrations. Yeah? And this allows, I introduce how to derive the entropy then. This allows to introduce at least the harmonic or vibrational entropy into the system. This way they try to cover also finer temperature. But I don't know from which temperature on normally these anharmonic contributions become important, not at very high temperatures only. I mean, you know, we all have thermal expansion even at low temperature or at ambient temperature.
But sometimes they also do simulations by taking the different lattice parameters.
Yeah.
And evaluate these properties and
Right, yeah.
assume that that corresponds to the higher temperature.
Right, yeah. But I'm not sure how you get then like vibrational entropy.
Yeah.
Maybe there are ways, I'm not an expert on this, but in general they have a very hard time. I mean, to construct a phase diagram, for example, I mean, they can very reliably predict which phases of a given material are stable at 0 Kelvin, but they have a hard time to predict how this changes with temperature, because then you have these entropy contributions. And of course, not only the vibrational entropy, but also the configurational entropy, which is not covered there. Okay.